Hello, everyone. This is going to be the second part of chapter 11. And last video, we were focusing on alkenes, but we only focused on a few things. One of them was naming. So we named a cis alkene and a trans alkene. And then we learned a new form of naming system, E or Z, right? And then we also learned how we made alkenes. So this was a good throwback to 40A with SN1, SN2, E1, E2 reactions. In this case, we are focusing on E1 reactions. We see this E1 reaction here. And we learned alkene substitution. So which one is the major product? Because in most cases, you'll have more than one hydrogen to choose from. And then we also learned about E2, or we reviewed about E2. Now, this video will be focusing on what you can do with alkenes, right? So last video we just made alkenes, but now we're going to be focusing on what specific chemistry they can do. Okay, so most of these will just be reactions. Most of them won't have a um, a uh, a reaction mechanism because it's a little too complicated for us at this point. But most of them will be ones that you have to know or remember. So yeah. So again, let's go back into what the alkene looks like, right? So we have this alkene right here. This carbon is double bonded to this carbon, right? And then I said that there was one sigma and one pi bond, right? And because of this, again, this is mostly stuff that you will learn in inorganic chemistry, but it's okay for me to just tell you it right now. Because it has this pi bond over here, it has this pi characteristic over here, it can react as a nucleophile. But the only thing is, this double bond will be a weak nucleophile, right? So if you remember, strong nucleophiles such as Grignard's, right? Grignard is a strong nucleophile. Let's do a reaction like this. The reason why it can easily react with this ketone is because this ketone has a delta positive, right? And this has a delta negative. Although this delta positive is not that big, it's only a minor delta positive, but it does not matter because we have a carbon nucleophile, which is a fully negative, which can easily attack it there and have that resonance, right? In this case, we have a weak nucleophile. So if you remember, water was one of our weak nucleophiles. And we saw water a lot of times in SN1 reactions, right? Where we had um, a, a carbocation. This carbocation makes up for the fact that this water is not that good of a nucleophile because this is a fully positive site, meaning it is a very good electrophile. So what I'm trying to hint at here is alkenes will most likely react with things that are highly positive or things that have that carbocation, right? So the first reaction that we will be looking at is just a simple, just like a memorization type of question. It's a reduction. So in this case, what if we want to turn an alkene into an alkane, right? You don't know any reactions like that. We know how to turn alkanes into alkenes. So the way we do that is we reduce it using a palladium. This is that PD on carbon. So it's a palladium metal on carbon, and it's a moiety. So we're reacting it with H2 gas, and it's under palladium on carbon. Again, you don't need to know the mechanism for this if I don't show it, but this is good to know because there will be synthesis questions where you are given an alkene and then you want it at the end to turn into an alkane. And this is how you do it. You react it with hydrogen gas, H2, and then it is on you place this alkene on a palladium on carbon um, species. So that is the first, it's a reduction. The second one is a hydrohalogenation, right? So here we have our alkene, and then here we have hydrochloric acid, right? The um, the most common acid that we'll see. So again, this has one pi bond and then one sigma bond. And because it's a double bond, it has an excess of electrons, right? And we can see that there's this big dipole difference between H and Cl. Cl has a huge delta negative and H has a huge delta positive, right? And that case, we can use this double bond to attack the H, right? And it's going to do that. But the only problem that we have here that we will run into is which, um, let me just do this, right? Where is the H going to go to, right? Because this carbon here, it's 1, 2, 3, 4, right? I'm just going to number it 1, 2, 3, 4. The double bond is shared between carbon 2 and carbon 4, right? If I drew this in a better representation, it's easier to see. See? Right? We can see that this carbon has 4 bonds, and then this carbon has 4 bonds as well. But we said that this double bond can react with a highly positive or a highly delta positive acid, right? Now, where is this H going to attach to? Is it going to attach to here, this carbon on the end, right? Or is it going to attach to this carbon on the left, right? As you can see, there are those two ways that the hydrogen can attach to. It can either attach here because, again, carbon 2 and carbon 4 are sharing that double bond, or it can attach to carbon number 2, right? So let's see. If it attaches to carbon number 4, as we can see here, this double bond is gone, and then this became an H. And now let's see who lost. This carbon stayed at 4 bonds, but this carbon went to 3 bonds. If we do a formal charge, carbon is 4 minus 1, 2, 3. So then we would have a carbocation right here, right? And uh, similarly, if we do it on the other carbon, if this second carbon grabbed the H, it has 1, 2, 3, 4, right? And then this one now has 3 instead of 4 with that double bond. So then we have a carbocation on the end, right? And then now this is where your 40A concept comes. Which one is the better carbocation? This one or this one, right? I hope you're shouting at your screen because it is going to be this first one because it is a tertiary carbocation versus a primary carbocation, right? So that means it's going to attach to here. The positive will be here, and then the hydrogen will attach to carbon number 4, right? And now, since now we have a positive carbocation and we have a negative chlorine, which just left, right? We can attach it, right? This has 8 lone pairs, so it's going to attach to there. And then, just like similarly to an SN1 reaction, this can attach both front and back. But in this case, this is not a chiral carbon, so we do not have to worry about it. But it attaches onto that carbon, right? Simple enough. So let's go on to how we can form alcohols with them, right? So here we have an alkene, again, with water, and we're reacting it under acidic conditions, right? So the first step is um, this water, it can't react with this alkene. This alkene can't react with the water because this electronegativity difference, although it is very large, um, we have a much larger acid in the way, right? So what's first going to happen is that the alkene will react with the acid, right? And then we saw from up above, thankfully, this is the same alkene as up above, right? Up above, the H will be on carbon number 4, which is right here. and then the carbocation will be on carbon number 2, right? So let's draw that here, H, and then we have this positive over here, right? And then look at what we have in solution. We have our water in solution, and we have a carbocation. This looks very, very familiar to an SN1 reaction, right? So it's going to attach here, right? And then once it attaches there, remember, it can attach both front and back side. And then let's do a quick formal charge on this oxygen over here. Now, this oxygen has a valence electron of 6. It has 3 bonds attached to it, and it has 2 electrons on it. So it's a positive, right? And then how do we get rid of a positive? We do something called deprotonation, right? In this case, we can use our water because in a reaction, we don't just have one droplet or one molecule of water. We have a lot of waters, right? So we have our water back. And then it's just going to grab the H and then push the electron towards the oxygen. And then we just formed our alcohol, right? And look at what we got back in advance. We just got back our acid, right? In this case, our acid was acting as a catalyst, right? It didn't change, it just helped the reaction proceed, and it helped that activation energy, right? So we form an alcohol. So that's just an alcohol formation from alkenes, right? And then the next one is a little weird. The next one is called halogenation, right? And the reason why we can do this is because under lab circumstance, this BR2 is really unstable, right? So it would much like much it would rather be a BR negatively charged than just this dibromine molecule, right? So what's gonna happen is um, so chemists in the past have done this reaction before, right? So typically, when you first see this and you learn everything up above, you would do the same thing. You would do this one attacks the BR, and then this one leaves, right? And then in that case, we would form our carbocation right on the edge over here, and then our bromine would be attached over here, right? And then there comes that problem that we're worried about, right? We have 2 nucleophiles to work with. We have a bromine that's a bromide ion that's freely floating around in solution, or we have the bromine that's attached to our molecule, right? And then the problem here is which one is going to attack? Is the higher energy bromide going to attack this carbocation, or is the closer bromine going to attack this carbocation, right? And that's the problem that a lot of chemists were dealing with in the past when they did this reaction. The fact is, none of these reactions actually happen. What's actually going on here is a specific reaction due to this moiety right here that we have. You see how we either have a close bromine that's in the same compound and can attack really closely, right? It's only 1 bond away, versus a highly charged bromide species, right? So because of this dichotomy between will the higher energy or will the closer one attack, it it doesn't happen if we do it in a lab setting, right? What actually happens is it's a pretty weird reaction, okay? So the end carbon will attack the bromine, right? Simultaneously, when that happens, this bromine will back attack the other carbon over here that it's attached to, right? And while that happens, the bromine leaves, right? So now you're thinking, what does this look like? This looks so weird, right? Well, it's actually not that difficult because it forms what we call what is really close to an epoxide, right? And that sort of makes sense. You see, this carbon will be attached to the bromine, but then this bromine wants to attack this other carbon. So then now we just have carbon 2 and carbon 4, right? One, two, three, four. Carbon 2 and carbon 4 are attached to the same bromine, right? And this is actually what we see in a lab setting. And this is actually what chemists in the past have witnessed, right? And now let's do a quick formal charge. Bromine has a valence electron of 7, right? It's a halogen. And it has 1, 2, 4, 6. It has 6. So then 7 minus 6 is a positive, right? And now we know that bromine is a very electronegative element, right? It really wants to be a negatively charged bromine, right? So then what happens here is you're going to open up this epoxide, right? It's not really an epoxide, more like a bromoxide. I don't know if you want to call it that. But it's going to attack the more hindered side, right? Remember, this is sort of like our positively charged oxygen, right? Because this bromine is positively charged, it's going to pull on electron density from the carbons that it's attached to. And this carbon has more groups attached to it, which means these groups are able to donate more electron density. So it's going to attack the more hindered carbon, right? So the more hindered carbon is the carbon number 2. Bromine attacks carbon number 2. As that happens, the bromoxide ring closes or opens up, right? This one goes to the bromine. And then what we form is the bromine here was opened up, right? Right there. And then this carbon now has the bromine over here, right? So now we just made a 2-bromine alkane, right? So the alkene attacked the bromine. The same time, the same bromine attacks the other carbon that has the alkene attached to it. And then this bromine left. We form an epoxide-like structure with this bromine in the center, and it's positively charged. As that happens, this bromine attacks the more hindered carbon, and the epoxide ring opens up, right? And then we form this. And the key here is that these two bromine species will always be trans to each other. So um, if this bromine was on a wedge, this one would be on a dash if there was stereochemistry, or vice versa, dash wedge. Or as you can see here, they're on the opposite side of the alkane as shown. This one's pointing up and this one's pointing down, right? I know that is a pretty difficult thing to understand because you never really see this, but theoretically, what was assumed where we did the same reaction above did not occur. So this was years and years of experimental data that showed that this is actually what's going on instead of this with H2O or with hydrochloric acid, right? So whenever you see any halogen, right, this can be bromine, chlorine, or fluorine, any halogen, this will occur. Okay. And then our last, second, or our next reaction is halogen underwater, right? So here you can see we only have a bit more. So let's move that down here, right? As you can see here, we have our dibromo species, right? This Br2. I should probably draw it out in this so it's easier to see. And then the only difference here is now we have a solvent. It's underwater. Here, we never had a solvent, right? So let's see what happens here. Again, whenever you see a halogen, this carbon on the end is going to attack the bromine. This bromine will attack the carbon that it's not that the carbon's not attacking, and then this bromine will leave. And then we form a a bromine like epoxide and Br, and we cannot forget our water, right? H2O. And then now this bromine is positively charged, right? Again, pattern recognition. We've done this before, so you don't. It's good for you to do the formal charge, but we've done this before, so it's just all about recognizing these patterns, right? And then now we know one of these molecules is going to attack. It's either the bromine or the water, right? It all comes down to which one is the better nucleophile, right? Give yourself a bit of time to answer this question because this is a very tricky question that might stump you. So, in experimental data, we can see that the water will be attacking this carbon over here and opening this ring up, right? So, let's first do that reaction and then I'll help explain, right? So, as that happens, that goes there, and then we're left with, again, these will be added trans to each other, right? This water is positively charged, right? But thankfully, we have a bromine here to clean up and deprotonate it. And then we made a molecule with a halogen and an alcohol, right? And again, these are trans to each other, okay? So let's go back. Let's see why this water attacks. Remember what nucleophiles are. Yes, we want them to be highly, highly negative, right? That's why a OH is a better nucleophile than a water, right? Because this negative charge makes it a better nucleophile. But the other thing about nucleophiles is nucleophiles are also sharing electrons, right? Look at what happened here. This oxygen had 4 pairs of electrons here, right? 2 lone pairs. But in here, I didn't show it. It only has now 2. So what it's doing is it's sharing the 2 electrons with this carbon. Now, let's think which element will be wanting to share electrons more. A highly electronegative or some element that's electronegative but not as big enough, but not as big as a halogen, right? And if you answer that question, you'll see why this water will be a better nucleophile than this bromine. Not to also mention the fact that this carbon is delta positively charged because this bromine is going to be pulling on the electron density, making this carbon easier to attack, right? And you can also see there might be some resonance going on here where this carbon is a positively charged carbon, right? So again, nucleophiles want to attack carbons, but they also have to share electrons. And for them to share electrons, they can't hold on to their electrons as tightly as a halogen would, right? So this water will attack that carbon. As that happens, this epoxide ring opens up. As the epoxide ring opens up, the bromine that just left is going to deprotonate and make a trans alcohol and bromine species, right? And we also have the HBr that we just got from right here, right? Give yourself some time to fully understand this. If you have any questions, please let me know. Um, but we'll be going on to our last 3 examples, which shouldn't be too hard. It's just remembering some solvents, right? So we learned that we can make alcohols, right? If you look from up here, we made alcohols already, right? Right here. But the only thing is this alcohol is on a tertiary, right? This alcohol it is a tertiary alcohol. What if we wanted to do some oxidation with that, right? So this tertiary alcohol cannot be oxidized by PCC or Jones, right? So how can we make the alcohol go to a less substituted carbon, right? And as you can see from all these other reactions, the main focus, this chlorine, this water, is on a more substituted carbon, right? This carbon has 1, 2, 3 tertiary versus a primary. So how can we do it where we want it to be on this carbon over here? Well, we use something called this boron species, right? This is actually called hydroboration. So what we can do is we can take this alkene, we treat it under BH3, and that's the first step. The second step is to treat it under hydrogen peroxide alongside a hydroxyl, and this can be in the form of NaOH or KOH or anything like that. What this does is it creates a alcohol on the least substituted carbon, right? If you remember from up top, if we do a H2O under acidic conditions, this will lead to an alcohol on the more substituted carbon, right? Because of the fact that we are going to have a carbocation on this tertiary, right? The only difference is this time we're putting it on that primary, right? So we use these two solvents, right? The next step is oxidation, right? So at the top, we form one alcohol, but what if we want to form two alcohols, right? If we want to form two alcohols, we can use something called KMNO4. This is going to be an oxidizing species. There is also another species called OSO4, an osmium species. As you can see, the difference is this O4. It doesn't matter at this point. It's not like a Jones versus PCC. But what this is going to form, it's going to form cis, right? They're on the same side, cis alcohols, or we can call this cis diols, right? Two alcohols, diols, right? So again, if you just put alkene under KMNO4 or OSO4, it's going to form these cis diols here. Last one is epoxidation, right? So you might have seen this in 40A, you might have not, but we can treat an alkene with MCPBA. It's one of the most common peroxy acids, or a peroxy acid, and it's going to form an epoxide under um, the two carbons here, right? It's going to do that. And this epoxide, as you may know from 40A, can do a lot of reactions. You can form trans diols, right? If you treat this underwater and acidic conditions, it's going to open up the epoxide ring and form trans diols, right? So I encourage you all to do this reaction at home for some review, as well as creating the opposite of a cis diol in a trans diol, right? So I know this was slightly long, but um, most of 40B will be like this. You will learn a lot of these reagents, and you're supposed to understand and remember them and keep them in your toolbox, right? For future synthesis type reactions or problems, right? I hope this was able to help you, and have a good week.